Hello, greetings, and welcome. So in this screencast, we are going to take a look at another shortest route problem. So it's going to take a slightly different form of some of the problems we've looked at so far, in that we are going to essentially set up and solve a problem to find the cheapest flight routes for us to take. Okay, and so basically, instead of distances, here we're going to use prices. So in this screencast, we will discuss and set up the problems, and then in a separate screencast, we'll solve. But in this case, my plan is only to solve part one when we solve it in Excel, because the rest of this will be left to you for your homework problem this week. So let's have some fun. So I'm planning a trip from city A to city D. Flights are available from three different airlines, X, Y, and Z. While a direct flight is available on airline X, flights are also available to cities B and C, and transfers between airlines may be made for $0. Find the least expensive shortest route from city A to D. And then 2, we're asked what if the transfer fee was $50 per transfer. And C, return to the case of $0, part 1. But what if we could only tolerate at most one transfer, or to put differently, add a constraint that the number of routes taken is at most 2. Okay, so let's go ahead and get it set up. Okay, so part 1 is a little tricky in terms of the setups could be a little different than we might imagine. So what I might think of, originally is, I could transfer. So if I start in, say, okay, so I'm going to start at some origin. Okay, so say my origin is my airport in city A. Okay, and so from the airport, say I would get on a flight from airline X, Y, or Z, and then I'm going to arrive at some terminal destination. Okay, and when I draw these paths, in theory, the cost associated with these paths is $0. Okay. Likewise, within essentially this airport in city, B and C, right? In theory, I could, have say some, add some additional node, which is the airport, at B. So, but it's just as probably better drawn in this way. I could readily change airlines while in those airports, and the cost of all of those paths is $0. And so I could write out some essentially complicated network to account for all of this. But it's not, really can't, because what happens is when we set up our shortest route problem, we're going to have 0, the cost, times some variable of whether or not we took that route. And so no matter what value that variable takes, right, that value is 0. And so that becomes a little problematic in our objective function. So what I'm going to do in part 1 is I'm going to do a little trick in which I'm going to consolidate my network. Okay, we'll have to come back to this in part B though. Okay, all right. So what's going to happen in part B is we're going to set this up. I'm going to consolidate my network. So let's call this part 1. Okay, I'm going to go from A. I'm going to have airport A, airport B, airport C, and airport D. All right, and we'll write this out in the general sense for part B or part 2 when we have $50 transfers, so you can see what that looks like. And you could try it out with $0 and see if you can get it to work. But initially for part 1, I'm going to consolidate it. Okay, and what I mean by that is when I look at our nodes A, B, and C. Okay, let's look at all possible connections. Okay, so and basically I'm not going to distinguish between X, Y, and Z because it doesn't cost me anything to switch airlines between X, Y, and Z. So when I look at A, okay, I have a route from A to B that's $160 and a route from A to B that's $170. Okay, so I could draw both routes on my essentially combined or consolidated diagram, but I know that if I had to choose between the two of these, right, if I'm definitely going to fly from A to B, I'm going to choose the cheaper one. Okay, so I'm just going to draw in a single route that's my $160 route from airline X because it's the cheapest. Okay, so that's A to B. Let's see. Now let's look at A to C. The only routes from A to C are an airline X, where that route is $90, and airline Z, where it's $140. Okay, so again, if I had to choose between two routes from A to C, I'm going to choose the one on airline X every time because it's cheaper. Okay, so from A to C, I'm just going to draw my single route, which is $90. Okay, so that's A to C. Do we have anything from A to D? I have one route from A to D, which is $400. Okay, so let's draw that in. Okay, so I have our one $400 flight from A to D. Next, we look at B. So I'm looking at flights originating at B and ending elsewhere. So in airline X, I don't have any. On airline Y, I have B to C and B to D. In Z, I just have one arriving at B from C. So leaving B, I just have B to C and B to D on airline Y. So B to C is $50. And C to D, or B to D is $80. Okay, and now let's look at C to D. From C to leaving C, the only flights leaving C are an airline Z, and I have C to B and C to D. So I have C to B, which is $30, and I have C to B is $30, and C to D is $160. Okay, so all I've done is I've taken all of our possible flights between the airports, combined them right in a single diagram interconnecting nodes A, B, and C, where when I have two flights from starting in the same origin and ending in the same destination, I only wrote down the cheapest flight because that would be the one chosen every time, since the transfer fee is $0. Okay, in B, we'll have to create a more involved network like this, in which we'll have to account for these interchanges, which are $50 in all of those cases. Okay. All right. Okay, so let's do it. Okay, so setting it up in this way. Okay, I'll start with my variables. Okay, so in terms of variables, okay, my possible routes is starting in A. I can go to B, C, or D. So I'll have XAB, XAC, and XAD. Starting in B, I can go to C, and I can go to D. Okay, I'm just looking at terminal destinations. Next, BD, XBC, and XBD. Okay, good. Then from C, okay, I have XCB, and I have XCD. Okay, there are no destinations leaving D. Okay, I'll start with my constraints. Okay, and actually let's start with what I'll call our general constraints. Okay, and so our general constraints, are going to be that all of our variables take on value of 0 or 1. Okay, so how we can force our variables to be binary is, I can list them all out. It'll be, say XAB, XAC, XAD, XBC, XBD, XCB, and XCD. Okay, they're all going to be greater than or equal to 0, our non-negativity constraint. Okay, and then I'm just going to say variables. Okay, so they're all going to be greater than or equal to 0, less than or equal to 1, and all of our variables are integers. Okay, cool. Okay, so there's our constraint that our variables are all 0 or 1. And then next, in terms of constraints, we're going to have our node balances. Okay, that's what we'll call our node balances. Okay. So what do we mean by node balances? Okay, so in terms of node balances, we're going to, let me go to my simplified picture. We're going to start with some fictitious unit, I guess I'd call it a passenger at A. Okay, so I'm going to add some input to my system at A, 1. Okay, and then my passenger is going to leave at B. Okay, so I'll write my node balances, and then after we do that, we'll write our objective function, which is going to be to minimize our cost. Okay. And so I'm going to have a node balance for node A, B, C, and then D. We'll write them all out. Okay, and our node balances will take the form of in equals out. Okay, so at A, okay, I have in is 1. Okay, and what's going out? Okay, I have flights, leaving to destinations B, C, and D. Oh, XAB plus XAC plus XAD. Okay, at node B, okay, I have flights leaving to go to C and to D, and then I also have a flight arriving from C. Okay, so in is coming from A and coming from C. So XAB and XCB. Okay, and what's leaving? AB's in, CB's in. Leaving is BC and BD. Okay. So B, 2 in and 2 out. Now if we go to C, we have flights arriving from A and B and leaving to go to B and D. Okay, I'm just trying to make sure. All right, so you have B, I see 4 lines. C, I have 4 lines. So coming in is from B and A. So we'll have XAC plus XBC. And flights out, we know we have 1 to B and then 1 to D. Okay, so from C, we have our flight to B and D. Okay, now looking at D, we have 3 arriving flights from A, B, and C. And coming out is that 1 unit. Cool. Okay, so there are our node balance constraints. Then finally, our objective is going to be to minimize our costs. Okay, and so in terms of minimizing our costs, we're just going to sum over all routes, and we're going to sum up the product of the cost of a route times that route variable, right? The 1 if it happens, 0 if it doesn't. Okay, so let me just, we're going to min, okay, and it's going to be z is equal to 160 XAB plus 90 XAC, then 400 XAD, okay, plus, okay, I'm going to write the next one on the next line so I don't run out of space. So I'm just going to follow kind of our variables from origin destination. BC is 50, BD is 80. And I've already forgotten. 50 and 80. 50 and 80. So 50 XBC plus 80 XBD. And then from C, 80 XBD. And then from C, we have C to B, which is 30, and C to D is 160. So C to B is 30. And then XCD is 160. My memory, 160. 160. Okay, so that's part one. So the goal would be to minimize our costs, which is found by this objective function. Subject to our constraints, we have our node balance constraints, and our constraint that our variables are essentially going to take on values of 0 and 1. And then just to summarize what we did is, since the transfer between airlines at our nodes is $0, we essentially just consolidated our network, so we had a single node A, B, C, and D. We didn't distinguish between airlines. And when we had equivalent flights from an origin to a destination, we just wrote down the least expensive flight, since that would be the one chosen, since we're trying to minimize our cost. Right? And in our node balance constraints, remember we have this fictitious unit, in this case, say a passenger, entering our network at A and exiting at D. Okay, so this would be part one. Okay, now I'm going to jump to part two, or part three. Okay, just because part three continues off of this. And in part three, we're asked, what if we could only tolerate at most one transfer? Put differently, add a constraint that the number of routes taken is at most 2. Okay, so we want to add a constraint so that we only take at most 3 routes. All right, so we haven't solved part 1 yet, but maybe the cheapest flights are found by taking 3 different flights, right? By taking 3 routes. What we want to do here is we want to add a constraint so that we restrict ourselves to either taking 1 or 2 flights. So either having 1 transfer or 0 transfers. And how we can do that is, remember, our variables correspond to 1 if a route's taken, 0 if it's not. Okay, so how I would know we have 2 transfers or 1 transfer and we're taking 2 routes is if 2 of my variables have values of 1 and all the others have 0. Right? If, say, XD was 1, all the other ones would be 0, because I would just be going directly from my origin to my destination. Um, if two of my variables had values of 1, all the others were 0, that means I have one transfer, I'm taking two routes. Okay, and so I want to make sure that I'm not taking more than two routes. And so what that would mean, okay, is that the sum of my variables needs to be less than or equal to 2. Okay, because when it's equal to 2, that means I took two routes, right? And I don't want to take more than two routes, which would correspond to having more than one transfer. So in part 3, we're going to, add we're going to add a constraint, and that constraint will be that the sum of my variables, okay, which again will be 1 if a route's taken, 0 if it's not, okay, needs to be less than or equal to 2. Okay, and that should be all that we need to add for that last part. Okay, so for part 3, that's all that we would need to add. Okay, cool. So I'm going to stop this recording because then what I'm going to do is I'm going to start a second recording for part 2, which will take us a little longer to set up. Okay, so I'll be back in a flash to start working on part 2.